I would like to introduce the first speaker, Professor Oleg Gendelman, professor of Technion University of Israel. Professor Gendelman is known for his outstanding works in the field of non-equilibrium statistical mechanics, nonlinear dynamics, and studies of anomalous energy transfer in low-dimensional systems. Please, Professor Gendelman, you can begin. You have approximately 35 minutes for the talk, and then we have time for discussions and questions. Please, you are very welcome.
Thank you. Thank you for inviting me to deliver this talk about Kapitza thermal resistance in linear chain models. So now I see from my window more or less what you see. Yes, unfortunately, I would prefer to to be with you, but okay, everybody knows everything. This work has been performed in collaboration with my PhD student Jidhu Paul, yes, at the Faculty of Mechanical Engineering in Technion. What is Kapitza boundary resistance? It is not less ubiquitous than normal bulk thermal conductivity, and it appears anywhere where you have some defects or some boundaries or whatsoever. So phenomenologically, if we have for bulk conductivity, we have some heat flux through the bulk with okay, normally believed linear temperature distribution with the length, and then we define the coefficient of bulk heat conductivity. Then for Kapitza resistance, okay, I hope, sorry. Okay, here, you see my pointer, yes? Do you see my pointer?
Yes.
Yes. So for Kapitza resistance, anyway, when we have some inclusion or defect, or when we have the interface, then phenomenologically, the temperature drops at the interface. And Kapitza resistance is defined as its temperature drop divided by the heat flux. The Kapitza resistance presumably has been mentioned the first time in 1936, well before Kapitza, yes. But as it usually happens, there is no scientific discovery that receives the name of real discoverer, are not principle. But Kapitza made most famous experiments to detect this phenomenon. This briefly the scheme of Kapitza experiment when you have the boundary between metal specimen and liquid helium, and you put thermopaste for measuring the temperature. Yes, it is possible to reveal this temperature drop at the interface. Now, there are many experimental results on Kapitza resistance, but I am more concerned about theoretical models. The first theory of Kapitza resistance appeared in 1952 by Isaac Markovich Khalatnikov. Unfortunately, he recently left us. And just to briefly summarize, there are two main models or two main perceptions of Kapitza resistance. The first one, acoustic mismatch model. It is normally applied for very low temperatures, and it assumes that if we have some interface which is defect-free, then we have phonon scattering according to Snell law. Yes, and phonons are treated as plane waves. Then there are many channels of reflection. The phonons can reflect, refract, etc. Yes, and then there is some transmission probability that is derived in certain assumptions of phonon distributions on both sides of the boundary. So this model assumes very large, very strong correlation between phonons and very few, very small scattering. For higher temperatures, it is more customary to use so-called diffuse mismatch model. Yes, this model adopts diffusive description of the phonon flux. Yes, all phonons are diffusively scattered in the interface, and acoustic correlations are assumed to be completely irrelevant. Yes, and then the transmission probability or the heat flux or temperature drop can be estimated from densities of phonon states on both sides of the boundary. Now, are these models good? Not always. Here you see some comparisons. This is thermal resistance of liquid helium at the boundary of this metal. You see that acoustic mismatch overestimates the Kapitza resistance by order of magnitude, and diffuse mismatch underestimates it. So it is not too accurate. Some more experimental results. This is at the boundary of two well polished metals. You see here that the trend is that the Kapitza resistance decreases with temperature. Say it is very different from thermal resistance. We know that heat conductivity decreases with the temperature, so we have a sort of opposite effect. For very low temperatures, we see that this is boundary between electropolished copper and liquid helium. This is something interesting. Here, it is the Kapitza resistance is multiplied by T cube to take into account quantum behavior of the heat capacity, and then we see almost constant values for low temperatures, and then decrease at higher temperatures. By the way, you see the predictions in both NMM and DMM fail by a lot. So, if we wanted to think how Kapitza resistance can be described in the simplest microscopic models, where we can try to get introspection into the system behavior on higher level than just semi-phenological models. So one-dimensional models are very relevant. Here I bring the picture known for heat conduction. Yes, that I think that everybody has seen this picture, and all of us know that, say, for linear model, bulk heat conductivity is undefined, and for nonlinear models, we can have divergent heat conductivity or convergent in other models. This is well known, but about Kapitza resistance, which, as I said, it is not less ubiquitous than bulk conductivity. It appears everywhere when you have some inclusion of boundary. It is not the case. Now, okay, why we care about one-dimensional models? Not only because of theoretical interest, but also because there are some physical systems that exhibit one-dimensional anomalies. Now, we want to try to treat the issue of Kapitza resistance at more macroscopic level. Yes, the ideal situation is if we will be able to derive the Kapitza resistance for some system from microscopic equations of motion. Yes, and physically we expect that Kapitza resistance is a property of surface or interface. It should depend on temperature and should not depend on the total system size. It should be local property, etc. Now, this question is not completely new. Yes. For instance, there was some work in 1978 when people considered the linear chain with different masses and stiffnesses. Yes, but the treatment was again semi-phenomenological. Yes, so they tried to use Khalatnikov-Ansatz to match numeric data, and their conclusion is there. Khalatnikov is not supported by the results of computer experiments. Okay, I would say that it's expectable. Now, what we do? First, we started with some numerics. We take here, we speak about big fragments. It is not one particle, of course. It is just an example of the sort of systems we look at. We have long chain with ends attached to the thermostats. Then we have large fragments that have some sort of inclusion, some sort of defect. And we expect to see this Kapitza drop at this defect. Then we observe all kinds of structures. We do numeric simulation and we compute the stationary state. It is in numerics. And in linear chain, we see all kinds of interesting phenomena. For instance, for heavy isotopic defect, we see this Kapitza drop. But for light isotopic defect, we have homogeneous chain and some light particle inside. We see something even more interesting. We see this drop of the temperature. There is also a difference. The Kapitza drop exists, but also we see this dip. We'll come back to it, and all this for explanation. Now, the good news is that we succeeded to solve this problem analytically, at least for linear chain. And I would like to briefly describe the approach. Here we consider first linear chain with two similar fragments, but here we have some linear time independent inclusion. Let us keep it generic for a while. Yes, and then the terminal particles from both sides are attached to thermostats. Then it is possible, then of course we take into account only the waves that belong to propagation zones of the fragments. We assume that the chain is long enough. So it is possible to write down the expressions for displacement fields in both parts of the chain. And if we have displacement fields, we can also derive the expressions for temperatures and heat fluxes. Heat fluxes are not even considered to be equal at this time, yes, because in general, this linear time independent inclusion can be also dissipative. Nothing prevents from it for a moment. Then this system can be solved. Yes, it is possible to satisfy boundary conditions. By the way, we assume that that only one thermostat has non-zero temperature. System is linear, so superposition works. It's okay. The central part of the treatment is that the parameters of heat fluxes from both sides of the inclusion are coupled by certain transfer metrics. Transfer metrics, we don't know a lot at this stage about it, but still we assume it exists, and it depends naturally only on the structure of the chain and the inclusion. And we can explicitly write down all coefficients that we have. Now, this transfer matrix, it turns out that it is far from being arbitrary, yes. So the shape of this transfer matrix is not arbitrary. It is governed by two principles. One of them is famous Rayleigh reciprocity theorem. it is easy to prove that this transfer matrix must have unit determinant. Yes, even by the way, even if there is dissipation. The next independent consideration is if we have no dissipation inside the inclusion. Yes, so again, it is linear, but no dissipation. Then the energy must be conserved, and we get additional relationships that the transfer matrix must obey. And after all, for conservative inclusion, we get very simple shape of this transfer matrix, generic for any sort of inclusion. It has three parameters, some x related to amplitude and two phase angles, mixing angles. But it is completely generic. Now, if the problem is solved and we can take our solutions and to plug them into the formulas for temperature and heat flux. Now heat flux is unique because there is energy conservation. Then we see that the answers depend on the length of the chain fragments, and 1 and 2. And at this stage, traditional procedure is to say that the length is very high. So for any finite value of the eigenvector, we can perform the average Qn, Qn1, Qn2 is rapidly oscillating phase, and we can average the result over this rapidly oscillating phase. So this is the transition to thermodynamic limit, to the limit of infinite chain length. But here, contrary to all problems, I think, considered before, here there is no one chain. There are two chain fragments that may be of different length. And it turns out that how we approach thermodynamic limit, we should take both lengths to infinity, but we can do that in different ways. And it was quite perplexing to learn that in this system, the result depends on how you approach the infinity. So for this problem, Kapitza resistance in linear chain with defect, no thermodynamical limit exists in strict mathematical sense. So it is a new situation because, for instance, for bulk conductivity, we know that something can converge in thermodynamic limit, something can diverge in thermodynamic limit, but here is the third possibility that universal limit doesn't exist and it depends how we approach it. So here you see that the result depends on the ratio between the length of the chain fragments, and if this limit is irrational, we get non-resonant case, and if R is rational, we get resonant case, and it depends. Okay, so for non-resonant case, then the ratio is irrational. We can just perform separate averaging of two rapidly oscillating phases. They are not locked, and we get expressions for the heat flux and for both temperatures. So this, as I said, it is for completely general shape of the inclusion. For a resonant case, the averaging will be in the case of the phase locking. For the simplest case of one-to-one resonance, it is possible to perform all integrations in the general case and to obtain the quadratures for all parameters of the problem. So this problem turns out to be analytically solvable both in non-resonant case and the case of one-to-one resonance. For more complicated resonances, the integrals are hardly doable. I'm not sure that it's possible to derive these closed form expressions. Now we come back to particular case of a single isotopic defect and a wide Gaussian noise. Here transfer matrix is relatively simple. And now we get explicit expressions. So in the case of one-to-one resonance, the integrals even can be evaluated in elementary functions, but these expressions are ugly. I'm not going to show you that to you. In the non-resonant case, the results are so different, yes, and it is so important that in this case, thermodynamic limit really doesn't exist. Now, to what extent it doesn't exist? We made some numeric simulation, just took the chain of total length 1000 and put defect at different sites. For instance, here you see the value of Kapitza resistance when the defect is on site 200, here in the middle, etc. So what you see that in most cases, for most defect placements, the measured simulated value is very close to average non-resonant value. But for strong resonances, there are strong outsiders. The strongest outsider is for one-to-one resonance, when the particle is exactly in the middle. And then you see here resonances 2 to 3, yes, some 1 to 4, etc. So it was surprising to see this resonance structure in this system, yes, and it is governed only by geometry. It means that frequencies don't play here any significant role, but geometrically we can have resonance and we can have no resonance. Even more than that, from these analytical formulas, we can easily plot the dependence of Kapitza resistance on, say, mass of the defect and on the friction thermostats. And we see that for resonant case means one-to-one resonance, yes, what we have. For resonant and non-resonant case, we see even qualitative difference. So non-resonant case exhibits non-analytic dependence on mass, and for resonant case, the dependence is analytic. So dependence on thermostats is also qualitatively different. It was a very interesting fact that here we have actually the third situation. Thermodynamic limit doesn't exist, and it is strongly exhibited in the properties of the system. Now, some brief comparison with linear models, nonlinear models, where we tried to assess all these factors. Majority of what we did for nonlinear models was for the resonant case when the particle is in the middle. Now for FPU, we get a bit noisy, but similar dependence, yes. But this result, when we tried also to study the dependence on the Kapitza resistance on the chain length, it struck us a little bit, and we don't understand it completely up to date. So in the FPU chain, we observed strong size dependence on the Kapitza resistance, which is somewhat frightening because we expect it to be local property. It is not. However, good news is that it is some new effect that experimentalists can try to look for in confined systems. So why exponents are so different? We think that it is just a crossover. What sort of crossover? For instance, if you look at the FPU chain in the limit of low temperatures, now 500 particles and the defect is placed on site 51, so it is closer to non-resonant regime. We see it for very low temperatures. This is the background non-resonant linear case. We see that for low temperatures, the FPU is very close to the linear. Yes, and then for higher temperatures, the divergence starts. So the length dependence, I believe, will be also involved with temperature dependence. But simulations are difficult. We are still in the middle of them. Then there is also I run briefly, depends on thermostats, etc. Now, interesting plot, temperature dependence. So you've seen it already, but for the FPU chain, we start from almost constant, almost temperature independent Kapitza resistance. And then nonlinearity becomes stronger and more involved, we get a decrease. Just for comparison, I don't claim that we can explain this dependence on the boundary between liquid helium and metal. Yes, but similarity is very interesting, and I want to think that this decrease of the Kapitza resistance is related to nonlinear effects. However, it is a big question to prove or disprove. Fine. One more interesting observation. Then I come back to this linear chain with isotopic defect when we see this thermal profile. It is a sort of scandal because it is apparent violation of the second law of thermodynamics. Here we have cold point and the heat runs in direction from left to right. So it runs from cold point to the hot point. Okay, clearly it is an anomaly of linear model, one of many anomalies. So linear model is so far from reality that it doesn't respect even the basic second law of thermodynamics. It is clear, and it is what we get also from analytics. So this result is definitely correct. But what happens if we switch on the linearity? It is interesting that for small time, after a million time steps, in the FPU, we also see this dip. Yes, you see it. Then, after 10 million steps, it is very less pronounced. And after billion steps, it's already completely healed. So, first of all, nonlinearity really helps to cure this violation of the second law, but not immediately. We see it only on large enough time scales, and of course this time scale depends on the temperature. For lower temperatures, it will take much more time to achieve it. So for short scale dynamics, linear models are good, and albeit they predict some strange phenomena. Okay, I'm not going into many other tales. No time. So in chain of rotators, we also observe the Kapitza step. And in this case, we don't observe any length dependence. So as bulk conductivity is normal, also Kapitza resistance is normal. The same for Frenkel Kontorova model, we also see some transition from small chain length, but then we see saturation, also normal Kapitza resistance. I wanted to say a few words about some complication. Originally, Kapitza resistance was formulated for the chain, for the case of the boundary, when we have two different fragments. So the analytic approach I described, it's possible to generalize it also for this case. When we have some linear time independent boundary between two different chain fragments. Different, I mean with different masses and different thicknesses. So very similar approach with the transfer matrix works. And here the the expression for transfer matrix is similar to the case of defect, besides this coefficient, which is related to the mismatch. Yes. In the sense, this case is even better than the case of single defect, because the relationship between eigenvectors for given frequency in different chain fragments is irrational. Therefore, there are no resonances, and we can look only at the resonant approximation, at the non-resonant approximation. So here, the illustration, we see that we take longer and longer chains, and Kapitza resistance converges to the background non-resonant value. Yes. What is put here, where we put the boundary in the specimen. At the ends, there is some noise, but I believe that for very long chains, it will still converge, as it does for shorter chains. Now, it is also possible to write down the explicit solution for general case. For the case of pure mass mismatch, it means that we have half of the chain, we have mass m1 and the other half is mass 1. The integrals are even more complicated, but still we can know everything what we want. Interesting observation is that in this case, the dependence of the resistance on the mass mismatch is singular. So we have here square root dependence, something that we have not seen in other cases. In nonlinear chains, we have some results that also show non-trivial dependence on the mass mismatch, but simulations are still in progress. Here we also, for linear chains, we also observe something similar for FPU. We observe size dependence and crossover. For chain of rotators, we observe sort of saturation. So from this side, the conclusions are quite similar. The models, it seems that the models that, nonlinear models that demonstrate abnormal heat conductivity demonstrate also abnormal Kapitza resistance. And the models with normal heat conductivity exhibit normal Kapitza resistance. Of course, we cannot prove this statement, but it is what comes from our observations for both the cases of inclusion, defect, and boundary. Actually, all cases when Kapitza resistance appears. Now, two conclusions. So, first of all, it is always nice to have exact solution. I think that, okay, frankly, I mean, I don't know, but I think that it is the only known case when one can derive exact expression for the Kapitza resistance in some systems. And it is nice to have exact conclusion or exact solution for comparison, especially as well-known phenomenological approach do not produce very good results. Then the division of one-dimensional models in static classes established for the bulk one-dimensional heat conduction is valid in certain sense also for Kapitza resistance. Then the next thing that surprised us a lot, as I said, was the non-existence of thermodynamical limit, or possible non-existence. So this geometrical resonance between different chain fragments, it is what violates the universality of the thermodynamical limit, and we see the difference. Indeed, Kapitza resistance can differ by 20–30%, depending on these resonance conditions. Now, the role of nonlinearity, yes, in the Kapitza resistance is absolutely crucial, because it introduces the temperature dependence, which is well known from experiments. Yes, so my assertion is that this decrease in Kapitza resistance with temperature, which is very universal in many experimentally observed systems, is due to nonlinearity. But okay, it is yet to be proved. Then it normalizes the heat flux and also can introduce the size dependence, non-locality. But all these issues should be studied in more details. Yes, then what we learned from this healing of the second law is that for short times, linear models are not just convenient models for analysis. If we are interested in short time processes, they can be used despite all problems related to them. Still, they give some short time predictions for the system dynamics. Okay, I think that my time is over. Thank you for your attention.
Professor Gendelman, thank you very, very much for very interesting lecture. I am myself very excited and fascinated about various things you have shown, and have a list of questions, but we will start from the audience. And we will start from Professor Gavrilov. He was the first. So please, Professor Gavrilov, your questions.
I have the following question about the number that change the behavior of the system. You said that this number can be rational or irrational.
Yes.
And, as I understand, initially this number is a ratio of two integers.
Right.
How it can be irrational?
Yes, but when you take both number, but it is very easy. If you take both numbers to infinity, you can choose the way that their ratio is irrational. Exactly as you approximate pi by the number pi by different by different rational approximations. So it is very easy to imagine. Imagine that you have as I said, if you just truncate any irrational number by some limited number of digits, you have the ratio, you have rational number, but when you take the limit, it will be irrational. However, as I demonstrated, it is mainly mathematical issue. Even for quite small systems, we get the values very close to this non-resonant limit. So when resonances are not too strong, it is not 1 to 1, 1 to 2, 3 to 2, etc. Even we have, say, ratio, I don't know, even 49 to 951, yes, something like this. It is irrational enough to get very nice accuracy from this non-resonant limit.
And this resonance is due to reflections or not?
Yes, this the resonance is because of phonon reflection. You have the resonance. You have the resonance between two chain fragments, right? And why?
Thank you.
And why? Because then you have two equal fragments. Then for equal frequencies, the wave numbers are also equal. When you have different chain fragments, then the wave numbers are not equal, and for different frequencies, the ratios between the wave numbers are different, so there are no resonances in this case.
Thank you. I understand.
Thank you, Professor Gavrilov. The second one was Mr. Leshkov, please.
Thank you, Mr. Gendelman, for your report. Open, please, slide number 14.
14. Okay, I'll try.
I haven't fully understood why is continuum special coordinate and dependence of group velocity on a continuum wave number is used before proceeding to the thermodynamic limit and in finite chain.
Maybe maybe I don't completely understand your question. So here in this slide, I speak only on the properties of transfer matrix. So Rayleigh-Roscoe theorem is valid for any linear systems, continuous, discrete, whatsoever. It's enough for the system to be linear, even dissipated, and Rayleigh-Roscoe theorem works. What does it mean? It means that if I apply force in one point and measure the steady state response in the other point, then if I will apply the steady state, the same force in the point 2, the steady state response in point 1 will be the same. That's all. And this theorem follows from actually from symmetry of the stiffness, mass, and damping matrices, and it's absolutely universal. So it doesn't matter, continuous or discrete. Energy conservation is also doesn't matter, continuous or discrete. So I don't see any restrictions from this side, if I understood correctly your question.
Thank you.
Okay, thank you, Mr. Leshkov. Now, please, Professor Anton Krivtsov.
Once more, Oleg, thank you very much. Very interesting lecture. And my question is, since this wonderful resonance effect is due to reflection of waves from the boundaries, can we conclude that in the systems where some kind of impurities could be taken into account, probably the most realistic values are given by the case where we have non-resonance case, where there is irrational ratio between the lengths of the chains.
Right, I think so. If you put the defect in the arbitrary place, then most probably you will not be close to strong resonance. And and when chain fragments are different, so when you have a boundary between two different media, then this resonance doesn't exhibit itself. Besides very special case of perfect matching, but this is not realistic.
Okay, thank you very much.
Thank you, Professor Krivtsov. Now, Professor Vitaly Pushkin.
Thank you very much, Oleg Valeryevich, for a very interesting presentation. May I ask you to show slide number 12? I think there was here, it's very nice analytical expressions for the temperatures. So my question is, maybe you can recommend some literature where I can find or maybe your papers where I can find the derivation of those expression. And the second question is, under what assumptions those expressions have been derived?
Okay, so the expressions for I'll explain. The expressions, it is easy to derive when you assume that at every frequency, the phase is random. Then only amplitude matters. The phase averages out, and then you get this, and then you get the simple expressions. So. So this is really an assumption of random phases, which is reasonable for any conceivable thermostat. And you can safely use it if you deal with white noise, as we later do it here. So if, for instance, yes, so I think it is possible to invent some say pathological forcing model, then it will be not valid, but it should be really pathological, because then actually this omega squared alpha 1 squared plus beta 1 squared, it follows from the fact that the component, the wave component, is I omega t. That's all.
So do I understand?
So what it follows that you look only at the waves in the propagation zone, and then we know very well the solution that of plenary waves. That's all.
So it is a steady state solution under the action of white noise, something like that.
Under action of something, but it's we don't need to specify here the type of thermostat. But the only claim is that say in these long chain fragments in the propagation zone we have only planary waves. And I think that it is a very reasonable statement, because it is what we have.
Yeah, it's very interesting. And can you recommend some literature where there is some kind of detailed derivation or something like that?
I don't think that that we did detailed derivation, because if you have planary wave, it is very easy to evaluate average kinetic temperature and average heat flux. You just average over the time period and you get it. So this derivation will take you exactly 2 lines. That's nothing to derive.
Okay, I understand. Thank you.
Thank you very much. I have myself a couple of questions. So on slide 6, you mentioned that conductivity either undefined or diverges. Did I understand correctly that undefined means infinite or not?
6, you mean? Yes. Here, conductivity undefined. In what sense? That the heat flux is proportional to the temperature difference, not to the temperature gradient. So we would say that heat conduction is proportional to the length, right? But I prefer to say it is undefined. By the other reason, because linear profile is not formed in this case. So it is not common picture of heat conduction. But
okay, thank you.
I think that it might be the question of terminology. If you prefer to say it diverges, I'm okay with it.
Because I thought if it's diverges on the right, it's also kind of not Fourier heat conduction, right?
Right. But again, I don't insist on precise terminology.
Okay. And on slide 28, you mentioned violation of second law. The question is it in a steady problem?
Yes.
Because in a transient problem, when this happens, well, first, it is surprising, but in inertial systems, it more or less can be understood. But in steady, it is very interesting in a steady problem.
So the solution, this is exact analytic solution for the steady problem. And of course, it is okay. I even would say that it is known. There are in my last paper in physical review devoted to these results, we also cite some previous works that observe this even for more complicated chains, for more complicated systems. It is known. Yes. So yes. It is another failure of a linear system.
Okay, this is and is it published? Can you share probably or direct us to the paper?
Okay. It's a bit difficult now. I have to look for in my computer.
But, okay. Then I will just.
It was my paper with Jitro Poll. It was published in PRE, I think about a month or two ago. Something.
Okay. Okay. Then I will find it.
It's very easy to find.
Okay. Then I will.
We can share. We have this paper.
Yes. Okay. Thank you very much. Okay, dear colleagues. So I would like to thank the speaker. Thank you very much again, Professor Gendelman.
Thank you. Thank you for inviting me.